All right, so in 5.3 we added to our list of special segments in a triangle, and in this case we talked about the angle bisectors. So what's the definition of an angle bisector?
A ray that bisects an angle.
Good, ray that bisects an angle. What's the theorem that we learned about the angle bisector? What's true about any point that's on the angle bisector? It's equidistant from the sides. So how do you know that it's showing distance to the sides? Good. True length is going to have a perpendicular line, right? So you're looking for the right angles. What's true about the three, what's it called, where the three angle bisectors in a triangle meet? In center. Circumcenter is perpendicular bisectors, okay? In center, right? And then what's the theorem we learned about the in-center? From the in-center to where would be equidistant? The vertices. In-center to vertices. So perpendicular bisector is circumcenter, and it's circumcenter to sides that are congruent. Angle bisector is in-center, and it's in-center to vertices that are congruent. All right, so if I look at number 1, this ray is a perpendicular, this ray has perpendicular segments to the sides that are congruent, which tells you what's true about that ray. It's an angle bisector. So what do I do with those two expressions? Set them equal to each other. So 3x plus 4 equals 4x minus 8. Subtract the 3, add the 8, and x is 12. Okay, 2 is now telling you the opposite, right? It's telling you that those are the angle bisector, or that is the angle bisector, and that the lengths from the point on the angle bisector to that side are congruent. What has to be true about that 4x plus 10? Has to be equal to 90 degrees. So in order for that to show true length, which is what would be equal, you'd have to have 4x plus 10 equals 90 degrees. So 4x would equal 80, and x would equal 20. Yep. So remember that any point is equidistant from the sides, but that little segment that connects the point to the side has to be perpendicular to the side of the angle. So when you're looking at an angle bisector, the segment that hits from the, from the point on the angle bisector to the side has to be perpendicular. Yep. Then it's not true length, and you don't know that they're equal. So this is the reverse of that. They're saying they are equal. If they are equal, then it is the true length, and they have to be that 90-degree angle. All right, so number 3 says point D is the in-center of triangle XYZ. This is why vocabulary is so important in this chapter. If that's a set of instructions and they're all blended in together, you have to know in-center means what? The middle of where? What type of segments? Angle bisectors. So if you mix that up with a perpendicular bisector, and today we're going to learn 2 more, then you don't know which theorems to use. So you've got to know in-center means angle bisectors, right? Which means that each of these little segments, these angles would be congruent. And from this point to the sides would be congruent. So I'm missing, those little blue segments would all be the same, right? But I don't have the length of a blue segment, which there was some like this in your homework, okay? And anybody learned the Pythagorean theorem before this year? Has anybody heard of that? Okay? So that's what you need in order to do this, which means this won't be on your quiz because we haven't covered it in class, okay? But it is a super valuable skill that you're going to use from here on out with math. The Pythagorean theorem says a squared plus b squared equals c squared. This works for every right triangle. A and B represent the legs of the triangle, and C is the hypotenuse. So this is going to be the longest side. So it doesn't matter which one you pick for B or A, but C has to be the longest side. So if I look at this little triangle, any of these triangles, but specifically this one, the hypotenuse would be which one? So 26 squared is going to equal 24 squared plus the side length that I'm missing, which is going to be B. So then I multiply it out. 24 times 24 And I get 576 plus b squared equals, and 26 times 26. 676. And then I solve for b, so I subtract the 576. And I square root. So what's the square root of 100? 10. So this little segment is 10, so it would be this segment, so it would be this segment. And dB is 10. By test time, possibly, but we would do more practice with it. Yeah. So, Mr. Carlson and I sat down yesterday, and he's a section behind us because he was out one day this week. So your quiz on Tuesday is just going to cover up to 5.3. We're going to move forward because I'm actually out next Friday, and it'll give him an opportunity to catch up. But your quiz on Tuesday will just be 5.1 to 5.3. So we're going to do 5.4 today, and then on Monday we'll review just 5.1 to 5.3. Okay, but just so you can get an idea of what's coming up. All right, so flip to the homework I did. All right, so 23 said in the diagram, N is the in-center of triangle GHJ, which segment cannot be deduced from the given information. So if I look at my triangle, if it's the in-center, it means that it's the meeting of the angle bisectors, and all of the blue segments would be congruent. So NM would equal LN would equal KN, which was one of these, right? It says that NM equals NK. That's true, so I can rule that one out. NL equals NM. That's true, so I can cross that one out. God bless you. Then I've got NG is equal to NJ. So you're trying to prove that this is congruent to this. Those are angle bisectors, so I don't know for sure that they're congruent, right? I don't know anything about their length. If you compare the three angle bisectors, those two might be similar, but the one on the other side looks like it's totally different. So then go to the next statement that says that HK, let me change the color. HK is congruent to HM. So these are the side lengths of the triangle, which I don't know for sure just by looking at them that they're congruent, but apply what you know about triangles. What's true about the two sides, the two blue sides of these two individual triangles? So if I look at this like it's one triangle, and this, oops, daisy. And this as though it's the other one. What's true about the lengths of these sides that I already know? This one and this one. Are they congruent? Yeah. How about the side that they shared? How about they both have a right angle? So what's true about those triangles? They're congruent. Why? Hypotenuse leg. And because they're congruent, CPCT would tell you that HM is congruent to HK, which rules this one out. And this is the only one you can't know for sure. You could not have proved those two triangles were congruent, the two little ones on the left. They have a shared side, but I don't know anything about any of the other pairing of sides. I've got a shared side and a right angle, but you don't know that the angle bisectors are the same, and you don't know that GL is congruent to LJ. Alexis.
Remember 25?
So 5.4 is going to add two additional special segments, and they are medians and altitudes. So by the end of today, you'll have had mid-segments, perpendicular bisectors, angle bisectors, medians, and altitudes. So my suggestion yesterday was to keep a running outline of those things. What are they? What do they look like? What's the theorem attached to it? What's it called where all three of those meet? And I would say to add to it with this one as well. So we start with a median. The median of the triangle is a segment whose endpoints are the vertex of the triangle and the midpoint of the opposite side. So median goes vertex to midpoint. Because each triangle has three vertices, each triangle has three medians. So there's the one that's already drawn there for you. from C to the midpoint of AB would be that median CD. If I was to go from A to the midpoint of CB, that would also be a median. And then the last one would be from B to the midpoint of AC. So if I was to construct a median, I would find the center of each line by measuring it with a ruler, cutting it in half, finding the halfway point, and then just drawing a segment that connects the vertex to that point. And the medians are concurrent. Just like everything else, these three medians hit at one point inside my triangle. The centroid is that point of concurrency. So circumcenter is perpendicular bisectors, in-center is angle bisectors, centroid is medians. And just like angle bisectors, the centroid is always inside the triangle. So the perpendicular bisectors are in, on, out. The angle bisectors and the medians are always inside. Doesn't matter if my triangle is acute, right, or obtuse. And then the centroid is also called the center of gravity because it's the point where a triangular region would balance. So if I literally had an object that was triangular in shape and I wanted to figure out how to balance it, I would find the centroid. I would draw the three medians, and where they intersect would be my centroid, and then that's where you would attach your base to. Okay, and concurrency of the medians of a triangle theorem. The medians of a triangle intersect at a point that is 2/3 the distance from each vertex to the midpoint of the opposite side. So this is the only one in which the segments are not equal. From the vertex to the centroid is 2/3 the length of the whole median. So if I look at the first one, AP, which is from the vertex to the centroid, is 2/3 the length of the whole, which is AE. BP is 2/3 the length of the whole, which is BF. And CP is 2/3 the length of the whole, which is CD. Which would mean what's true about this little segment, or this little segment, or this little segment. If the other part is 2/3, what's that part? 1/3. Does that make sense? Okay. All right, so this says in triangle LMN, RL is 21, so this side length, or this median is 21, SQ is 4. It wants you to find LS and NQ. So if RL is the whole side length, how do I find LS? Good. LS equals 2/3 of R, or LR. So LS equals 2/3 of 21. 3 goes into 21 7 times. 2 times 7 is 14. And then NQ. So this time I've got SQ, which is which portion of that median? The 1/3. So how do I find if SQ equals 1/3 of NQ? How can I find, oh, so it's 4, sorry. How can I find NQ? Yep. Good, multiply times 3. So if they give you the big part, it's 2/3. If they give you the little part, it's 1/3. Okay, this one says a sculptor is shaping a triangular piece of iron that will balance on the point of the cone. At what coordinates will the triangular region balance? So how do I know where it's going to balance? It's in the, what's the point called? Centroid. How do I find the centroid of this? I got to find the medians. You can find where they intersect. Sure. It's a little challenging. You'd have to find the equation of each of those lines and then figure out their center. So can you think of a different way to do it? You do have to find at least one median. No, you can't just eyeball it. Yeah. So you can find the median by finding, how would I draw just the median, let's just say? How would I draw a median of any of these? Good. I got to find the midpoint of one of the segments. You with me? And then I would connect it. So let's start there. Pick a side to find the, or pick an angle to find the median of. Which one? Doesn't matter. If there's three of them, it won't matter, right? Say again? Well, they're all 2 points. Okay, so we're going to find the midpoint of this segment here. How do I find midpoint? Nope. Nope.
It's x plus x1 plus x2 over y2.
Not over.
Over
2.
You divide it by 2.
Yes. Midpoint. Add the 2 x's, divide by 2. Add the 2 y's, divide by 2. Don't make it harder than it is. So this would be 16 over 2, which is 8. This would be 13 over 2. Oh, we picked a yucky one. Midpoint formula? Chapter 1. Yep.
You just
Add them and divide by 2. Remember, things in geometry never go away. Can I give you a hint on which ones I would have picked? Ones that when you add them, they are even. So I don't get a fraction.
This one's not that bad because you can kind of see where it hits 6.5 on the line.
Yeah, but you're not done. You've got to use the distance formula to find the length and then do 2/3 of it. Yeah, so it gets ugly. So what I would have picked is the ones on the left, because if I add 6 and 8, I get what? 14 is 14. Oops, I went ahead. Is 14 divisible by 2? Yeah, so 14 divisible by 2 would give me 7. And then if I add 6 and 2, I get 8 divisible by 2, and I get at least 2 whole numbers to start with. So if you can, you may not always, but if you can get an even number, stick with that side. So I'm going to find the midpoint of this side, which is 7, 4. So 7, 1, 2, 3, 4, which is that point right there. And this would be my median. Now, how do I know where the mid-center of this triangle would be? I'm sorry, the centroid of this triangle. It'd be not the middle, but on that segment, it would be where?
Wait, isn't the x already there?
No.
Why not? The line going through the middle?
Yeah, but you don't have the other 3. You'd have to do all 3. If you did it that way, you'd have to do all 3. 8 and 7.5, which would be here. And then you'd have to find the third side. If you're doing it the way you're talking, you'd have to find the midpoint of all 3 sides. So then I would do 10 plus 8 divided by 2, and 7 plus 2 divided by 2, 18 divided by 2, which is 9, and 9 divided by 2. So 9 and 4 1/2, which is here. And then I have to connect them. Now, do you see your centroid? Yeah. And it's on a nice round whole number, right?
Yeah, but couldn't you see it off the first one?
No. You can eyeball it, but that's not, you can't eyeball anything in geometry, right? So the intersection there would be, what's the point? 8, 5. So if you couldn't find it, if it didn't fall on an exact spot, then it gets really challenging, because you'd have to find the distance from each point to its midpoint to find the length of the actual median. You'd have to multiply it times 2/3 to get the distance for where you'd need to be, and then find your coordinate point that way, okay? So I think in the one in the homework, it falls just like this one, where it does fall on an exact point. Otherwise, things get kind of ugly. It's still possible to find it, just a lot of work. A triangle is the last special segment. So mid-segment, perpendicular bisector, angle bisector, median, and now altitude. The altitude of a triangle is the perpendicular segment from a vertex to the line containing the opposite side. Every triangle has 3 altitudes because it has 3 vertices. And like a perpendicular bisector, the altitudes can be in, on, or outside. In if it's acute, on if it's right, outside if it's obtuse. Okay, so let's think that this is a triangle. What kind of triangle does this appear to be? Acute, right? So if I call this A, B, C, if I wanted to find the altitude of this triangle and I start with the vertex of A, then I go from that vertex to the other side and I would form a right angle. So it's got to start at the vertex, and it's got to go to the right side, and it's got to have a right angle. That's an altitude. So that would be A, okay, C, somewhere about there, because you want it to be perpendicular, and B, somewhere about there. Again, you need it to be perpendicular. So if I had actually measured those angles with a protractor and found exactly 90 degrees, you would have found these 3 points meet. And in an acute triangle, they're going to meet inside the triangle. Now let's say I do the same thing with a right triangle. Okay, in a right triangle, if I were to start with A and I were to draw a segment that goes to the other side at a right angle, where is it? It's actually AC, so it's actually the side that's already there. So if I go vertex to the opposite side of a right triangle, it's going to be the leg. And the same thing's going to happen on the other side. If I try to connect B to the other side, it's also going to be the right angle. And then C would be something like this. The 3 points meet, or the 3 segments meet. And on a right triangle, where they meet is on the triangle. Questions so far? Yep.
It's on, like that one is there when it's on the triangle because there's still no other line.
Could there still be? Not other altitudes. Those will be the 3 altitudes. So in a right triangle, 2 of the altitudes are going to be the legs. Yeah. Nick. Because it has to be perpendicular. So from A to the side opposite at a right angle is AC, which is the side of the triangle. So then the hardest one, and I don't want you to stress out about it because we're not going to do constructions just yet, but I want you to understand it. The hardest one is the obtuse triangle. Just like with perpendicular bisectors, the perpendicular bisector's hardest one is the obtuse triangle. The same is true for an altitude. So if I go from A to the side opposite. So if I were to draw lines like this, do any of those hit the side opposite at a right angle? No, which is why the definition of a median, of an altitude says, or the line containing the side opposite. Because what I have to do is actually extend out this side to get a segment that starts at A and is perpendicular to the other side. So this is going to go outside your triangle. If I do the same thing with B, again, none of these segments are going to be perpendicular. So I have to extend this side and then go from B. C is the only one that when I draw it, it actually hits the side. So the obtuse angle in an obtuse triangle is the only one that would actually have a segment that connects the opposite side without having to extend it. So as these are, do they meet? Which would mean I'd have to extend them. So this would extend, and this would extend. And that's why when we talk about obtuse, they meet outside. So the medians and the angle bisectors are always inside, but the perpendicular bisectors and the altitudes, the two that have a right angle, right, both of them have that perpendicular part to it, they both meet in, on, out. In for acute, on for right, and out for obtuse. So you would not be constructing it, but you do need to know that they do meet different places, okay, depending on the type of segment. All right, and the orthocenter. So this is the last point of concurrency. The altitudes meet at a point called the orthocenter. Sometimes the orthocenter is inside the triangle, sometimes it's on the triangle, and sometimes it's outside the triangle. So when would the orthocenter be on the triangle? If it's a right triangle. When would it be outside the triangle? Obtuse, and inside? Acute. Questions so far? Okay. Find the orthocenter of triangle QYZ, or sorry, XYZ, with the vertices that are given. So the first thing I want you to do is plot those vertices. So X is 3, -2. Y is 3, 6. And Z is 7, 1. Actually, I shouldn't put that yet. So what appears to be true about this triangle? What kind of triangle does it look like? Oh, it's borderline acute and what? Right. So if it's acute, then my orthocenter is somewhere in the middle of this triangle, and I would have absolutely no way of finding it unless I took out a compass, measured my right angle, drew the line, measured my right angle, drew the line, measured my left. I wouldn't be able to do it. So in a case like this, most likely that's going to be a right triangle because we now know that that orthocenter would meet where on the right triangle? On the triangle, specifically if you look back. So we're going to know that this meets here. How could we confirm it's a right triangle? The slope of the two legs. So the slope of YZ would be 1 minus 6 over 7 minus 3, which is -5/4. And the slope of XZ would be 1 minus a -2, which becomes 3 over 7 minus 3. Wait a minute, what did I just do wrong? 3/4. Did I do the first one right? This is YZ. 1 minus 6 and 7 minus, oh, so they're not. This is not a right triangle. So this is not a right triangle. If it was a right triangle, those two would be perpendicular. Do we understand that? And if they're perpendicular, what would be true about their slopes? Opposite reciprocal. So the fact that they're not means that this is not a right triangle. So then these points in here, let's see if I can erase just this one. In order to find them, I would need to form perpendicular segment here, perpendicular segment here, perpendicular segment here, and then find that point, which appears to be 6, 1. Okay? But there's no relationship of these lines. So to do something like this, you would need to find that right angle, which means you could use a protractor. Okay? So you can pull in a transparent protractor, put it right on top, and look at your right angle. If you were doing this on a piece of paper, which I'm not going to make you construct it on a test or a quiz, but if you were, then you would literally just use your piece of paper with a protractor, look for that right angle, and draw the line. So when we do have time for constructions, which I think will be in 2 weeks, we'll do a lot of stuff with this. Again, you're not going to be assessed on it. It's not going to be a test, okay? But it is good to get to know how to do things like this. Okay, questions on any of 5.1 to 5.4? So again, my advice to you is to outline of 5.1, which was your mid-segments, 5.2, which is your perpendicular bisectors, 5.3, which is your angle bisectors, and now you can add to it 5.4. So I would go through definition of what the special segment is, the point of concurrency. Everyone has one except for the mid-segments, like the first section. And then the theorem that applies to the point of concurrency, which every one except for mid-segments and altitudes have. So there's a theorem for an angle bisector, perpendicular bisectors, and for medians. Make sure you're keeping a running. And where do they meet? In, on, or out kind of a thing. Okay? So that you're not trying to slam it all in the night before. So make sure that you know each of these for all the segments. So mid-segment's the only one that they don't all meet, right? What was the mid-segment? Do you remember? What's a mid-segment? Whoa, hasn't been that long. What's a mid-segment? The one that connects the midpoints of the sides, right? So that's a mid-segment. That's a mid-segment. That's a mid-segment. And what's the theorem about mid-segments? They're parallel to the third side and half its length. Okay? So that's the only one that doesn't meet, but it still has a theorem that applies to it. All of the rest of them meet, have a point of concurrency. There's a name to the point of concurrency. And then all of them except for altitudes have a theorem relating to their point of concurrency. Okay? Perpendicular bisectors are congruent from the perpendicular bisector or where it meets to the vertices. Angle bisectors are congruent from where they meet to the sides. Medians are the 2/3 the length. Altitude's the only one you don't know anything about.